Okay, so now let us start the next lecture, and that is so not that I have given all the three dimensional problem, you know everything. I have given only a representative, a simple three dimensional problem, how to tackle it, and it is a real, we deal with it every day. So, without making assumption, how to solve a three dimensional plate, which is very thick, no assumptions are made, and it can be solved analytically. So, this problem could be solved only in 1970, which is hardly how many years, 45 years. So, 45 years old, finite element also is started 45 years, about 60, 56, 60. Then there is another technique that is started around the same time, it is called, see, design, any design is not unique. Somebody will take depth of the beam as 1 meter, next person will take only 800, somebody will take 120 and then design the remaining reinforcement, other things, it is up to you. So, design can be hundreds depending upon your choice, so then this idea came, especially in aerospace structures. We are getting designs because most of the structures are very complex, so they used to do it on the basis of thumb rule. So, by then by 1960s some new methods have developed, finite element came which could be tackled, which could tackle any complex problem. Then people said, why not optimize the design? Why not get a design which is either optimum weight or optimum cost? Okay, optimum cost means lowest cost, or lowest means reasonable cost. Lowest may not be meeting your requirement. So, something which meets your requirement, you come to near lowest. So, civil engineering, it is not minimum weight that governs the design, it is the cost which governs the design, civil engineering structures. While in aerospace, it is not the cost, but it is the weight. Weight is very important in aerospace. If you can reduce the weight, yes, that structure will be much more efficient, it can go higher, it can go longer. So, weight is their consideration. So, this also started discussion on this plus methodology, how to choose out of 1000 solutions that is possible, how to get the one is doing manually. People used to do manually 10 solutions, then choosing the one among the 10, but 10 was not the solution. People say no, there are only so many, so why not choose from the infinite? So, then one branch of science started optimization technique. It is a mathematical tool, how to optimize, how to get minimum. In mathematics we find out what is the minimum of a function. So, it is a function of function, your problem is there are so many things. So, it is a functional which we minimize. So, here we minimize a functional. So, anyway, that mathematical theory developed, started coming up only around that time in a very big way. So, when we had just finished our graduation, finite element, matrix method, because matrix method first it came, matrix method became because of computers, whole theory was written in terms of matrices, because matrices is the language of computer. Giving a matrix, it is very easy, Aij, I going from 1 to 100, j going from, and then give all the elements. Computer will read and put it in proper location. So, that became, so all the structural theory was written in matrix form. Slope deflection method was written in matrix form around that time. We started solving. Then finite element for continuum. So, all these three I told you, finite element, optimization, and what else did I say? One more. No, I did not say one more. Then the third thing that came around the same time, I mean that area, I mean that year, I mean decade was very fertile. So, other thing came that new material, people were obsessed with isotropic material until 1960. All books were only with isotropic material, only steel, aluminum, wood, whatever it is isotropic, nothing beyond it. Then the things started, no, we can have a material which is orthotropic, which is anisotropic, which can be layered. Layered pressure vessels started around the same time. How to fabricate a layered pressure vessel? Number of layers of not the same steel, but different steel plates were glued together to form a pressure vessel. So, this material started orthotropic, and then came this another breakthrough came that polymer composite material, polymeric material which are very moldable, and then they were reinforced with fibers to make it stronger in one direction and weak in other, but then if you have number of layers of such, so it will be all right. So, layered polymeric material started around the same time, and we gave the name composite material or layered composite material. Each layer itself is composite, there is a fiber embedded in each layer sheet, then number of sheets were joined together. So, development of fiber reinforced composite material came. So, all the theory became non-isotropic. This is started only in 1960. So, you can imagine how many things is started in around matrix method, finite element, then immediately after matrix method came finite element, then optimization because of this, and third was use of new materials, layered composite started, then this composite material came. And actually this problem was solved, this 3D problem which I told you, Pagano and Srinivas, they solved it because they started hearing this composite material has come, but then there is no solution. Isotropic people would not have been interested in solving this 3D problem, but because it was a composite material and it was very difficult to find out stresses and strain in composite material. Plate and theory is there, but then that will give approximate. So, they wanted to benchmark the plate solution. They could get something from plate solution, but then they did not have any benchmark solution, better solution than plate solution. So, in order to benchmark the plate solution, this work of Srinivas and Pagano, they form very important development. I mean, it is very, now you can say it is all routine, what is there, but when it was first time done, then it is great. Just like Navier solution, you can say now it is okay. Any function can be represented, product of 2 sine cosine and then solve reduce. So, Navier presented in 1800 something, around 1900 I think he presented, I will give you the date sometimes. So, but now, so this history is very important. Whenever you study anything, please go into the history, then it will give you the motive. Yes, this is because of this happened, because people were stuck. Composite material came, layered material came, they did not know how to validate their results. All the solutions were there, they were approximate, and there were a lot of difference between the various methods. So, they wanted to have a benchmark, yes, this is the correct solution, you now benchmark all your other solutions with reference to this. So, then this, because that was the time no person will work in this analytical solution, because computers and finite elements had come, everybody as a bandwagon, they were working in FEM. Why would any person work in analytical solution in an era which was having so much fertility in computational methods of finite element. So, this also was unusual. My teacher was there in Kanpur, so he became Professor N.C. Nigam. After computers came, he was very unhappy. He said people are not working anything analytical. People are going and just solving by as a number, they are not getting any feeling. But then this work defies that. Even in the era of computers, these two persons worked in a non-computer oriented area, because they wanted to give the benchmark solution. Okay, so this is what happens. Now, so there are many problems in real life which are in reality you can see that they are two dimensional in nature. So, if you realize that such problems which are physically two dimensional, their behavior is two dimensional, then why to use three dimensional theory? Then it is foolish. Then it will be foolish to use three dimensional theory for a physical problem which is behaving, a real behavior is two dimensional. So, two dimensional problems. Now, obviously, two dimensional problem, once they are two dimensional, so that means it becomes a plane problem, plane. All the points are at least they are lying in a plane. It will be function of z will disappear, it will be only, let us say, function of x and y. Everything will be varying only around a plane. So, it will be plane problem, PLANE na, plane function of only two independent So, dependent variable, that means any dependent variable dependent variables means this is the response when the problem is there, when the loads are applied, loads also will be two dimensional, not three dimensional, and even the response means displacement, forces, stresses, everything will be two dimensional. So, both load and dependent variables will be 2D. 2D means function of, say, function of x and y. Z let us forget. So, we will write everything in terms of. Now, what are these problems? So, I have something that I have prepared. So, large category of problems of the theory of velocity which are important for practical applications. So, now these large classes, I am trying to say what are these. These problems give rise to considerable simplification in mathematical model and the theory, and thereby of course it is solution, in essence, the problem definition becomes independent of one of the coordinate axes. I have already explained, say z axis, and as such problems do exist in physical world. I am emphasizing only that. It is not that we are making any approximation, they exist in physical world. Such problems fall under two categories. One is called plane strain and other is called plane stress problem. There are two categories, plane strain and plane stress problem. Now, what are these? Plane strain. Here one of the displacements, say W, is observed to be 0 everywhere, and the other two displacements, that is u and v, are seen to be independent of z coordinate. It is possible. I mean, I am just saying, which corresponds to, so z coordinate. So, plane strain, yes, plane strain. So, u and v are seen to be independent of z coordinate, which corresponds to the w displacement. I mean, z will correspond to w displacement, that is I have a. Thus, the following things will happen: plane strain, yes, plane strain, yes. I mean, that is u will be function of x y, v will be, and w will be throughout the body. But I will like you to, so one is this, displacement will be like this. Now, plane strain, but then as the name indicates, why it is plane strain? Plane strain, out of 6 components of strain that we have got, it will so happen that only strain components corresponding to xy plane, will be existing in this problem, if you take it like this. So, u will be there, v will be there, but w every will be 0, and then so plane strain, see, out of 6 components, you have a, what exists or what is not 0 is only epsilon x, extension in x direction, extension in y direction, and shear in the same plane, shear xy plane only. You take a small element around point P, and how does that element gets distorted? That means this. This gives you distortion. This will keep the element in at right angle only. A square will become rectangle, but here it becomes distorted. Gamma angle between x and y axis will occur. So, it becomes like this, and these 3 stress components, these 3 strain components, do not talk of stress. When you are describing plane strain, we should not bring in the word stress. We should talk only in terms of displacements and strains. This is, you please take it from me, this is very important, and because we find these simple things, we ask the PhD candidates for Viva OC, and most of the time they fumble. Simple thing. When they will describe plane strain, they will say stress, something happens to the stress. When they will ask you plane stress, then they will say something happens to the strain. Why are you talking strain, bringing in strain in plane stress? So, do not bring in that, only have strain. So, these 3 strain components which are perpendicular to the plane x y, they are all 0. I have just written. The above equations show that all displacements and deformations take place only in one plane. So, this is very important. only in one plane, that is xy plane, of course, one plane. Such deformations of course, deformation can be plural also, because number are, but here I have written single word, such a deformation, such deformations, such a deformation. Okay, deformation is change in shape, etc., everything general is called plane strain. In case of, now when does this happen? So, then there are some examples. Plane strain, one is dam. Dam, every cross section of a water dam is in state of plane strain. Every cross section of the dam, which is very long, dam is fixed between two hills, so that water does not flow and it gets retained. So, if you see every cross section here, the loading is more or less similar along the length, and if not on the entire length, at least in the central portion loading is similar. Everywhere it is the same depth, same water pressure, every cross section is undergoing, and the behavior of every cross section also is similar. So, this dimension, the length dimension of a dam is immaterial. This problem can be thought of as only in one plane, because you analyze only one simple slice of the dam, one delta z. You cut one slice in the middle and show all the forces acting on it, because this plane will remain plane. Plane is always, otherwise compatibility will not be satisfied. So, every plane is plane. No strain, no epsilon z, if z is the direction of length, no epsilon z exists, epsilon z I am saying, not sigma z. So, epsilon z is not there, it is always a plane, original plane, at the same point it has to remain, otherwise it cannot move on to the left or to the right. Any plane cannot move to the left, it is not possible, it must stay at the same place. Okay. So, the dam is a good example of plane strain. Then another example is, you take a cylinder, full cylinder or hollow cylinder subjected to symmetric load, put a hollow cylinder in water vertically, not horizontally, vertically. Water will be acting on all the surface, both inside the hollow also it will be acting like this, from outside it will be acting. These are independent of theta. Every angle it is the same water pressure. So, the ring, any circle ring which is there in the cylinder will always remain a circle. It will not get distorted. Circle, any circle you draw, right from the inner radius to outer radius, you can take any circle, you will find that circle has only become either elongated, radius has changed, it has become shortened or it has become more, but it has not become ellipse. So, this cross section theta equal to constant, any theta, you will see will always remain plane. At any, you cut any cylinder from the radial line, radial plane, and expose it, it will always remain plane, it cannot get distorted. So, both in the case of dam and cylindrical body, such I think I have already explained both of these. This is like this, this cylinder is like this, vertical symmetric loading. So, I need not consider this length of the cylinder, only one ring is enough, because behavior is same anywhere. Behavior of this cylinder subjected to external load is same, therefore, I just take one slice this thickness of this cylinder, width of this cylinder perpendicular to the plane of this paper is very small. I have taken some delta z, and so I need to consider only this. Similarly, in this dam is very this dam cross section is very long, but then I need to consider only this because it is representative. Everywhere similar thing is happening. So, why should we consider 3 dimension? They are already 2 dimension. Although physically they look 3 dimension, but behavior is 2 dimension. So, such problems are plane strain, not plane stress. This is what you have to, here I have only explained, there is nothing, explanation is there. Now, I am trying to bring in the mathematics or simplification of the elasticity equations, how it comes. In the case of dam, if this z dimension, the length dimension, there is no change, no particle in the cross section is moving to the left or to the right along the length of the dam. In that case, epsilon z has to be 0. And what is epsilon z? See, I have written here the longitudinal ends 0 and L are constrained. So, are constrained to move in z direction, they are not constrained, they are constrained to move means no movement. Then from the constitutive relation epsilon z is written as sigma z by E. This is for isotropic material, but we can also write orthotropic or anything, does not matter. So, this is plane, it is plane, cross section is plane. So, this one must be 0, and from setting up this is the constitutive relation, one of the constitutive relation, 3D constitutive relation. So, we have set it, thus a non-zero sigma z equal to from here 0. So, sigma z is becomes equal to nu times sigma x plus sigma y. In the cross section, because it is constrained at the 2 end, yes, there will be stress in this direction, normal stress, which is same throughout, it is independent of z. So, everywhere it is the same stress, and the value of this stress sigma z is this. If you can find out sigma x and sigma y planar stress, just multiplied by nu, then it will be. So, I am taking the name of stress only now by setting this. When I set this equal to 0, this gives me a relationship, this is equal to 0. So, this becomes equal to nu times this. So, in a plane strain case, the normal stress perpendicular to the plane which you are considering is present, and in the entire plane its value is constant, no change. Plane strain, and it is a function of only then it is also, this sentence is okay, but what is more important is this. One can directly see that under these physical conditions, our basic group of 3-dimensional elasticity equations will considerably get simplified because of this. And the constitutive relation, especially since we have started with this. So, let us see what happens to the constitutive. The constitutive relations will look like the following set. Since sigma z equal to this nu times this, therefore, you take the first constitutive relation. First is what? This is our first isotropic constitutive relation. Now, sigma z here, which is there on the right hand side, there are 3 quantities, but sigma z is only a function of this. So, it can be eliminated. So, you just substitute here sigma z equal to, so it becomes nu square by E sigma x plus sigma y. So, right hand side is only function of sigma x and sigma y, sigma z can be eliminated, and then your epsilon x becomes like this. Epsilon x, just see here, epsilon x is a function of sigma x and sigma y, but then these coefficients get changed because we have substituted, we have eliminated now. Clear? So, sigma x will become like this, and similarly, sorry, epsilon x is like this, and similarly even epsilon y. There are so many ways of writing this. So, one. So many ways. First one, this one. So, this is this, you got it this. Now, it is only in terms of sigma x and sigma y, epsilon x, because this can be eliminated. So, now this is rewritten here, this one is rewritten here, rewritten in this form. You see 1 plus nu here, 1 plus nu and 1 minus nu is 1 minus nu square. There is also 1 plus nu here. So, I take 1 plus nu by E common. So, whatever remains in the bracket is this. So, this is a epsilon x become equal to this. Similarly, epsilon y will become this, just change of, this is already there, this does not exist, it is due to physics of the problem. Problem itself is such that this is 0. So, 3 components, this is the third component. So, this is not there. What about epsilon x y? Epsilon x y, yes, within the plane particles can move, xy plane particles can move. Once they can move, a rectangle will become distorted, a square will become again parallelepiped or distorted. So, this will there. What about this? This happens, what is this angle? If this is the z plane, see, if this is the my this palm is the cross section of the dam. So, this is the remaining plane. So, this is my z direction, this is my z direction, this is x direction, this is y direction. This angle is always remaining 90, always, under all circumstances, any point you take here, this between x and z and y and z, this red pen is z. So, it is always remaining 90 degree, that means no shear angle, no shear in this plane and no shear in this plane. So, these two also become 0, again due to physics of the problem, due to physics of the problem. So, 1, 2, 3, due to real problem. So, there is no approximation. Do not think that we are approximating 3-dimensional problem to 2-dimensional. The problem itself in nature is such, this nature is such, loading is such, dimension is such that this 0, this is 0, this is 0. So, I am left only with 3 strain component, and thus our obviously things will become, life will become much simpler. And therefore, for plane strain, material constitutive relation or the generalized Hooke's law as we call it, for the plane strain case can be written concisely in this form. This is written in black ink for isotropic. This is majority of, although we have covered material properties other than isotropic also, which we can write for plane stress, plane strain. Rajeshwar, you are sleeping. and Vishnu Priya is not writing. C will depend on the C deep notes, which you can get directly. But writing helps. Let me tell you, writing, unless you write anything, even if you are reading, because this is a technical subject, it is not history and geography. Unless you write, whatever you read, you have to write on a piece of paper, then only it enters into your head, not by just reading. No, open the book and then read, nothing will go, it will disappear from your mind. So, you must write. So, writing is a good habit and keep that up. Okay. So, this is these three relations can be written in an alternative form also. I do not know why I have written in so many. Yes, because there are so many ways in which the same thing can be done. Is this why alternative form? Because this is our standard way of writing. If you write, this is how we have written our Hooke's law. General 3-dimensional Hooke's law, how we have written. So, we are changing the elastic constants. This elastic constant, this all this, that means this multiplied by this divided by this 1 minus nu square by E is equal to yes, 1 minus nu square by E is equal to 1 by E star. So, ये किया है मैंने E, then inside. So, I have written here these are the new elastic constants. They are defined in terms of E and nu only. These are two new elastic constants. Further, the inverse relation, that is, see, I told you always, it is always better to write fundamentally. Strain can be written in terms of stresses from physics. This is what I have been explaining. This relation can always be 3-dimensional. I am talking of 3-dimensional, very easy to write. This has become special. So, that is why we have written in the same form, the way we write 3-dimensional. So, we have defined. So, but then the form that is used in analysis is always the inverse. Stresses as a function of strain you have to always have. So, whenever you write your dissertation or anything, please define your first constitutive relation in this form, because this is the fundamental form, and only as a second step you please write in. Many people write in that directly stress as a, in terms of strains. Then we get doubt what are the elastic constants, because you should understand what is the meaning of E star, what is the meaning of nu star, etc. So, we do not know there. So, this form is always, so a starting point always is this form, then you please convert. So, the inverse relation, that is stress, they can be written inverse. Inverse means I want to find out this and this. Of course, the last one is very easy, but always, so you have to solve two equations. So, what I do, I add these two by multiplying the second equation by nu star. Multiply the second equation by nu star. Why do I add this? So that I eliminate one of the two. If this is also yes. See, I have multiplied this by nu. See, this can be done. You can see here between these two, just below this. Epsilon x plus nu times epsilon y, nu times. So, nu times kar dijiye. So, nu times and nu times. See, there is already nu times here and plus nu times here. So, this and this will get cancelled. Why we do this? This nu times sigma y, and then I am multiplying this by nu. So, the idea is to eliminate. So, I will be left with this, and so right hand side will become only sigma x, and therefore, sigma x will become yes, it is coming this, and similarly sigma y, if you do the other way, sigma y can be found out as this and tau x y as this. So, these are your, from these it so happens that in this problem sigma z just is present, it is not 0. I have already explained, no? Sigma z is there in plane strain. So, what is the value of sigma z? Nu times this plus this. So, that must be kept in mind, but it is not an independent thing. Once you have found out from your analysis, so this is all is important. This one can always be is a dependent relation. This is a not a independent relation, not independent relation. Is it? Are you able to see here this one? This one is not independent relation. It is a dependent on, so, but then you must not forget that yes, sigma z will be 0. So, in a plane strain, 3 strain planar strain components are present, then 4 stresses, 4 stress components, 3 planar stress components and 1 transverse normal stress perpendicular to the plane xy also stress is present. So, 4 components of stress and 3 components of strains are present in plane strain. It is not 3 and 3, 3 strains, this I mean 3 strains only, that is epsilon x, epsilon y and gamma xy, but stress, when it comes to stress, when it comes to plane strain, we are talking of only plane strain. I have not gone to any other thing, no, just plane strain. We are giving everything a plane strain. Okay, so this is plane strain. Last relation can be written in terms of, last relation means that dependent relation. We are talking of this one, we are talking of this, can be also written, because just for uniformity, everything is in terms of star here. So, why not write this also E star, nu star. So, this also can be written in. So, last, since nu star is this, so this is simple. I have done all this, you see, it is very simple, cross product this into this. So, nu is equal to nu star minus nu star nu. Therefore, I can get nu in terms of nu star. Okay. Thus, the longitudinal normal stress can be written in terms of nu star, because replace nu with nu star. So, this is okay. So, this is not important, but yes, it is completeness. Now, what I write? We can also write stresses in terms of strains in terms of original engineering constants E and nu. Anyway, this is substitute, it just pure substitution. Anyway, it is all given in very long hand, every step is there. So, I have got now my sigma x is given by this. Sigma x, the expression for sigma x, E divided by 1 plus nu, 1 minus 2 nu, within bracket 1 minus nu epsilon x nu epsilon y. Similarly, sigma y will be equal to this, and tau x y of course will be there, and sigma this. I do not know why I have written, so much is not required. but those who believe in just formula, for them it is okay. But those who believe in deriving everything from first principle, this is not required. If you know at one place, the first step that epsilon z, gamma zx and gamma zy, they are 0. Out of 6 strain component, these are 0, rest all follows. You write it in any manner that you can manipulate, that is more important. 3 dimension you, but yes, but you must know the 3 dimensional Hooke's law. 3D Hooke's law, basic Hooke's law, strain in terms of stresses must be known. Then from there you just put these 3 conditions, you will get this, everything, whatever I have written. So, whatever is all is padding, is not basic material. So, something I have written to summarize the constitutive relation for plane strain case can be written, to summarize the constitutive relations for plane strain case can be written in 2 alternative forms. Oh God, plane, PLANE. This I have already derived now. This, it can be written in this one, and normal stress, which is a dependent quantity, is this, and the other one is other alternative form. Everything you write in terms of star. And the engineering, and these are, by the way, these are, we are writing equations in terms of engineering elastic constants. If you write in terms of Lamé elastic constant, that means lambda and mu, that also is possible. You do not write in engineering constant, but you write in terms of lambda and mu as mathematicians, because this is a, see, solid mechanics is also a course in advanced level MSc in mathematics. They study behavior of solid, but then they do not understand physics of the solid. They understand only mathematics of the solid. Okay. So, they have this Lamé constants, which comes in the elasticity matrix. While we understand, we know engineering constants, so we write in terms of engineering, but then Lamé constants also you must know. I think I have already given you earlier what are the relationships, how to convert into Lamé, lambda and mu, not nu but mu. Mu is same as g, so that is, but then lambda is little complicated, so that you should see. So, here engineering elastic constants, that is E and nu, are related to the mathematical, E star, nu star are mathematical constants, they have no meaning physically, by the following relations. This you already have seen, inverse also is there, this you have seen, yes. So, there is nothing. So, that is what I am saying, there is unnecessarily too much. So, therefore, it is clear from the above that all non-vanishing stresses, stress are 4 components, 1, 2, 3 plus this dependent, which depends upon this and this. It is not independent, but it is there. And these are all independent of z coordinate. And therefore, see, compared to this plane stress, I will just finish in 2 pages, because that Okay. There is a book in matrix method of structure analysis. See, matrix methods is just precursor to finite element method. First, matrix method came only for framed structures, for trusses, for rigid frames, how to view as these frames, because it was started by, see, FEM was started by civil engineer. So, first they learned matrix method, how to convert normal slope deflection equation in matrices, then how to write uh, stiffnesses of various individual elements separately and then combine all of them together. So, first they did it for framed structures. Framed means rigid frame, continuous beam, trusses, things like that. And they did not realize that this can be extended also to continuum solid. See, structure is, in structures we study only skeletal structure. Skeletal means, in between it's all hollow. You have just frames, a truss member or a rigid frame member. While in solid you have continuity, continuous, no gap. So, finite element people are these structural engineers were well versed in that part, matrix method of skeletal structures. So, when it comes to solving a continuum problem, a plane stress like plane strain problem, a two dimensional, how to solve this, then they were on a firmer ground. They knew the basic theory, they had to only extend, again this was in the early years, this plane strain problem was transformed into not plane, into equivalent truss structure. There are papers, there are people who have worked how to find out the equivalence by creating gaps in between. If you have a plane strain problem, how it can be done as a continuous, as a truss, integrated truss without equivalent properties of the truss member were found out, because we knew how to analyze truss, but we did not know how to analyze this continuum. So, it could be solved by matrix method if you can find out the equivalent, and then finally the breakthrough came, I can treat continuum structure as such itself by FEM. In 1956, which year did it come? See, anything comes, the date of publication is very important. So, especially for research scholars, see, do not think that publications are not important. You would not be taking the name of Srinivas or Pagano if they had not published. They would have solved the problem, kept quiet. Next person also would have solved somewhere by taking their, somebody meets them, then they will get the idea. That was the old, guru kya bolte the, Gurukul, you go to a guru and then the disciple will learn directly from guru, and then it will remain there only, unless there is another set of disciples. But here the idea of publishing came, okay, it goes into a larger audience throughout the world. So, people know, yes, this problem has been solved. So, this is publication is extremely important, date of publication is very important, okay, and good journal is again very important, because only good journals go throughout the world. The journal published in Hyderabad or in Agra, they somehow remain only in that city. Okay, there are many journals now being published from Hyderabad. Just to beat these teachers, they devise, how to beat the system. Teachers requirement has become, everybody become must must become professor. Sorry, must have a PhD. Every teacher of a higher education department must become a PhD. This was not a requirement in early days. There were very good people, very good researchers, very good workers. They never had their own PhDs, but they produced so many PhDs. There are history, there are number of people, very good people without PhD producing very good papers, joint papers with the students, but they themselves did not have any research degree. So, that was through motivation, but now UGC makes it compulsory. No, if you want to remain in teaching, you must get a degree. So, this has lowered the, it is lowering the standards of the scholarship, because now people are being forced somehow to get a degree. So, especially small universities, state universities, somehow they manage to get a degree, and this is one way. You publish in some local journal and say that I have published. I went to Hyderabad, JNTU. One assistant professor, he came for interview for professor for review. He claimed, he was so naive, he did not understand what is good paper, good journal, good. No sir, I have started a journal. I have started a journal. So, he brought, sir, I have published 200 papers, because then he was counting all the papers that were printed in. Since I have started, I have published 200 papers. Very good. So, this is not a scholarship. Scholarship, you work and your work should be known throughout the world. So, this is, please do not publish in those journals. Okay. So, okay. So, this is equilibrium equation is okay. Boundary conditions. I mean, I am trying to define the complete problem. The surface conditions get simplified. So, this is now instead of 3, we will have only 2. 2 is stress and 2 displacement. So, either this or this on the boundary. Boundary is like this now, na? Boundary will be, so either this on the edge, which defines the domain of the problem total. So, on the edge you will have either u or v. Bar means prescribed. So, either this is prescribed or the corresponding stress is prescribed. Now, strain displacement relation will be only these 3, because you do not have W, you have only U and V. So, only these 3. So, from 6 they get reduced to 3. Then compatibility conditions of strain, which comes by eliminating this UV and getting a relationship only in strain. Okay, compatibility. See how many compatibility equations we have in 3 dimension? 6 are there. Here it turns out to be only 1. There exists only the first of the 6 conditions of continuity or compatibility equation, and it relates this. All 5 become 0. So, it very much gets simplified. So, you have now equilibrium equations, strain displacement, compatibility, constitutive relation. I think we had a long discussion constitutive. So, everything is covered for 2 dimensional plane strain. So, the problem is completely described. Okay. So, yes. So, above derivations complete the mathematical model of what? what I have written here, top of what is this? Two-dimensional plane strain elasticity, and one can proceed from here to various solution strategies. Now, equations are known, so how to solve this is the next one. So, plane strain is completely covered in 21 pages. So we will stop here. You please come at 2 o'clock.